Send them to my email. Hi, hi class. This is Biven. I just got back from the Immersion 2017. This is John and I. It was awesome to take a lot of pictures yesterday. If you happen to have any of them and you got some time, I'd love to have them. You just send them to my email. If you were there, I know we had a blast. It was awesome. If you were not there, you're going to have a blast at your immersion. So I just want to give you a quick introduction to these Unit 11 slides coming out after the immersion. Everybody's fired up. And of course, we're always fired up about statistics. And we're going to continue on our discussion with regression with log transformations. And that's what you kind of looked at in the videos and probably already started the homework in Unit 11. But that's what we're going to look at. Stay tuned. I got 5 short videos to make up for this week's live session, just because the immersion was on Thursday. So enjoy, and I'll see you next week. All right, later. Hi, and welcome to the beginning of Unit 11. At this point, you've already seen some videos, and you may have already started the homework, but we want to go through a quick presentation on the residuals, what a residual is, how can we look at some residual plots, model assessment, a little bit of that. Simple linear regression, specifically in doing transformations and then interpreting the coefficients after these transformations, specifically the log transformation. That's what we want to handle in this section. So let's go ahead and get started. Awesome. So this is primarily in Chapter 8. We want to look at a closer look at assumptions and how we can, if we don't have our assumptions met, how we can do these log transformations that a lot of times get the assumptions met, so we can use the framework of simple linear regression. The beauty of the log transformation specifically is it has a really great interpretation. We don't lose a lot of interpretation after that transformation like we would with potentially a lot of other transformations, like an x squared or square root of x, or some other transformation that we may have that's not as interpretable. So keep an eye out for that. Remembering our assumptions, we have the linearity, meaning the straight line of means, that the means of those normal distributions conditional on x for those subpopulations of x, those means are linearly related. Notice that outliers might bias estimates, might bias p-values, might influence and affect p-values, confidence intervals, and so forth. So regression is sensitive because the mean, regression is an estimate of the mean, and the mean is sensitive to extreme values, to outliers. So the whole regression framework here can be very sensitive to outliers. Constant variance, we're assuming that for every subpopulation of x, so conditional on the x, the normal distributions of the response all have the same standard deviation. You'll see that here in a little bit mathematically. We want to check for that. Normality, again, in order to have the normal distributions have the same standard deviation, they have to be normal distributions. So we are modeling with that line, we're modeling the mean of a normal distribution of y's for each subpopulation of x. And thus, around the regression line, we're assuming that there's a normal distribution. Conditional on x, we're assuming that those y values are normally distributed with that mean around the mean. And then we're going to assume independence, that each pair is independent of any other pair. Otherwise said, each observation is independent of every other observation. Note, we're not saying, of course we're not testing to see or assuming that x is independent of y. We're relying on that linear correlation to help us build this regression model. So we're trying to harness the correlation between x and y, but we're assuming that each observation is independent of one another. Great, so what might we have? This one looks pretty good. This is kind of the ideal situation we want to have for simple linear regression. We have an x on the x-axis and the y is on the y-axis. And we have an even scatter of points for each value of x. We have about an even scatter of points around that regression line. Looks like normality is set, looks like constant variance is set. We're going to assess that with the residual plot a little bit later, but for sure this one looks ready-made for simple linear regression. So okay, so how about this plot? If we remember, we always want to plot the data first. We want to look at a scatter plot. We look at this scatter plot and we see this. And this looks like for each, as x gets bigger, for each subpopulation of x, but as x increases, it looks like there's a curved relationship between the mean of these normal distributions in x. It's not a linear relationship like we see here. As x gets bigger, the mean of these normal distributions are linearly related to x. In this case, it looks like there's a curve. No problem. It doesn't mean we throw out the simple linear regression or multiple linear regression when we get their framework. It just means we might have to do some transformation. And when you have the means being having a curvilinear relationship such as this, we want to transform the x. Notice that conditional, you can see from those little box plots or range indicators there, is the standard deviation per x, conditional on x, pick any x and look at the estimated standard deviation, are about the same. Going across here, they're about the same for any x, but certainly the means are curved. Moving on, here's another example of curved means that you'll see quite often. This would be a good candidate for an x squared. This is kind of a parabolic relationship. Certainly not linear, and certainly remember this, think about it, what kind of linear correlation coefficient R would this whole data set have? If you're looking at the correlation between x and y, it would be about 0. But clearly does not mean, again, as a review, that there is no relationship. It just means that the relationship is not well approximated with a linear relationship. So this one, no problem, we can transform x to x squared. And if we actually plotted y versus x squared, that would have a much more linear look to it. Again, here noticing that the standard deviations for each conditional x are about equal. So let's see some examples where they're not. Here's one right here. Now the means are curved, and it looks like as x increases, the standard deviation around that mean is increasing as well. We have a very good idea of where y is going to be down here, and a much more uncertain idea of where y is going to be here. We can see these bars are much wider than they are down there. In that case, when we have increasing standard deviation and a curved mean, transforming y a lot of times will help. Again, this isn't a silver bullet. These are how it's kind of presented in the book. I want to really underline the fact that that doesn't mean that transforming y is going to work. It's very much a trial and error effort. So keep giving it a shot, but that's that. So a lot of time you want to transform y here. So moving on, you can see a lot of different kind of scatter plots, but this is one that you may come across. The means, looks like standard deviation is about the same. The means are linear, but the normal distribution, this really kind of highlights what I mean by normal distribution of x conditional on y. Notice that for each x, let's consider this x right here, it looks like there's a very much right skewed distribution, right? It looks like there's a big hump here, and then it levels off. There is a probability being out here of being very far from the mean, but that's not symmetric over here. So if you can think about this kind of vertically, the distributions, this would be very much a right skewed distribution. All you can do here, simple linear regression is great. If you're trying to estimate the mean, this is going to be a good model for you. If you're trying to do prediction intervals or something, then you may want to look somewhere else, because the confidence intervals of an individual is very easy to get a higher y up here than it is to get a y this far from the mean. So, so again, for prediction intervals, not so good. For mean, simple linear regression will work great. Simply report this skewness, and you should be doing okay. Good work. How about this one? This one we have even means. The means are all linearly related to x, but the standard deviation is increasing. One thing we're going to cover in the second course is weighted regression. That is an option here where you actually weight each point based on its perceived variance or its estimated variance. This point here has a much higher variance than this point down here. So we can simply weight that smaller when we're estimating the beta naughts and beta ones in this case. Not saying that a transformation may help you out here. In fact, a log-log transformation that we're about to study very well may help you out in this situation. So transforming x and y may help you out here. Again, it's very much a trial and error process. Great. So last thing I want to do in this small video here is to talk about a residual. Remember, this might be our scatter plot. We can kind of see here that the standard deviation is increasing. Doesn't look like there's too much curve in the data. Maybe we could see that. But a lot of times, subtracting out the mean, meaning let's just look at the distance each observation is from the regression line. How well, what is that residual? Oftentimes, taking the mean out and just looking at the residual helps us diagnose increasing standard, non-equal standard deviation, be it increasing or decreasing or some other kind. But and also normality and curve trend. So what we might want to look at instead is the residual plot, which is, it should be a default output of nearly any software package. So this is, of course, SAS. We can see that there is some evidence of increasing standard deviation. Checking this point out way up here, that's really evidence of increasing standard deviation, or maybe an outlier, probably an error or an outlier from some other population that somehow got into our data set. But however, whatever it is, you can see it. A lot of times you can see the curvature much neater. You can diagnose things easier with the residual plot. Remembering the residual is simply the observed value minus the expected, the dot minus the line in terms of y. And mathematically it can be written like this. That's just our observed y from our data set, and that's our line. That's our regression equation. Actually, that is a plus in there. So you can consider that a plus sign. I'll change that before I put the slides out there. Checking these out, here's just another couple examples of some residual plots. So this is the scatter plot, and it's its corresponding residual plot. You can see, when you get really trained, you can see it from here, but much easier to see in the residual plot. There's curved trend in the mean, and extreme evidence of increasing standard deviation as x is increasing, non-constant or heteroskedasticity. There's a crazy word for you. Heteroskedasticity is also different standard deviation. This one, of course, is increasing as x is increasing. So last thing you want to see here, or maybe last couple slides, is this is our regression equation. If the assumptions are met, then this is how we're looking at it from the residual point of view. This is the error. If the assumptions are met, the errors should be normally distributed. Notice that the errors are normally distributed with different mean, right, mu I, and the same standard deviation. So this is not sigma I. We're not allowing sigma to change based on where we are, what observation we're on, what number of observation, or where we are on the x-axis. Sigma should be the same, but we're modeling mu based on where we are on the x-axis. Each EI can be estimated with the residual. That's what a residual is basically EI hat. So here we have a plot that looks like the assumptions are all met. We look at the residual plot. That's what it should look like. An even scatter around 0. And that's what we're checking here. An even scatter showing that linear trend, since it's the residuals with respect to a line, linear trend is appropriate. And also equal standard deviation can be diagnosed with this plot as well. And remember that we also want to have normal distributions of our residuals. And you can look at a histogram, what we'll see in the next slide. But this is our QQ plot that we've studied before, and a very nice looking normal QQ plot, and that's a QQ plot of the residuals. This will all be standard output of SAS, and you can very easily get it from R, Python, whatever else you're using, Minitab, Stata, so on and so forth. So here we have very high evidence that residuals are normally distributed, or at least not a lot of evidence against it. So finally, we have the regression panel. We're going to learn all about these plots. This is the fit diagnostics for a certain model. So this is the residual plot. It's the same one we saw before. Same exact one as this one right here. So it's just a small version of that. And this is our QQ plot that we just saw on the last one too. This one I didn't put on the last one, but this is the histogram. You can see a fairly normal looking histogram. We're going to look at these other ones as well. So in future units, we're going to get very familiar with these guys, with the rest of them, specifically these three up top here. These are influential statistics trying to identify outliers, as is this one. I'm going to touch on leverage a little bit later, even though it was brought up in Unit 11. Leverage you can think of is just a function of how far the observation is from the observation's x is from x bar. The observation's explanatory variable is from the mean of all the explanatory variables. So leverage has nothing to do with y, the response. It has everything to do with the explanatory variable. And the farther out that value is from X bar, the more leverage it has. But to really get a feel for leverage, we have to have an idea of the studentized residual, and we'll put them both together to get Cook's D. So just a little commercial and heads up of what's to come. But how do you get this plot? It comes default in procreg. As far as SAS is concerned, you just run procreg. It'll output it there for you. And you put in, for procglm, you have to put plots equals all. And of course, you're going to put solution here. But procglm is a much more general procedure. Basically, all the functionality of procreg is inside of procglm, but you have to tell it that you want plots equals all in order to get this plot, but you'll get it. So plots equals all there. So when we come back on the next video, we're going to look at different transformations, 3 different transformations in particular, 4 if we consider just the linear model that we have. That would be called like an identity transformation, where there really is no transformation. But we can look at a linear in Y log transformation. So that linear log is when we're talking about linear in the response and log in the explanatory. We can look at log linear when we only transform the response with a log transform and leave X as is, don't transform X as all. Or we can transform both and do a log-log transform. And that's what we see here. What was I going to say there? Those are the ones that we're going to look at. We're going to look at how to interpret those. And there's one more thing, but I'll bring it up in another video. Excellent work on this one. I'll see you in the next video. Hi, welcome back to Unit 11, talking about log transformations. We are going to look at the first one that we're going to check out is the log linear model. So let's go ahead and look at it. I believe this is one you've seen before. This is an example from the book. It's an industrial laboratory under uniform conditions. Batches of electrical insulating fluid were subjected to constant voltages until the insulating property of the fluids broke down. Very interesting study. 7 different voltage levels spaced 2 kilovolts apart from 26 to 38 kilovolts were studied. The measured responses were the time in minutes until breakdown. So we're measuring the breakdown time of this insulating property. And we're trying to see if it's related to the amount of electricity, kilovolts, that we're running through the fluid. So here are an example. Here's a little snippet of our 76 observations. So we have the time to breakdown of the insulating property of the insulation versus the voltage that we were at. So we have a lot of repeat observations, lots of 26, lots of 28, lots of 30, so on and so forth. So there's our data. We're always going to plot our data. We can get a lot from that plot. We're also going to look at our residual plot, and we can see that for low voltages, there's evidence of high standard deviation of this time. Whereas for high voltages, there's very low standard deviation. And not only that, but it also looks like the mean time it takes to break down is somewhat is not linear. It looks like it is maybe somehow curved. It looks like it might be a little bit higher for low voltages, and then it kind of does not have a linear trend in its decay or in its shortening mean time. So we have a little problem with linearity, and we have a little problem with constant standard deviation. So if we go back to those, since we have a problem with constant standard deviation, we go back to those diagnosis plots from the first video. We see that maybe we want to try, again, trial and error. We'd like to try a log transformation on the Y. We might try it on a couple different ones or try different transformations. But the first one that we might try to start off with is with that. And lo and behold, this is after, you can note, a log transformation. Awesome. So we do that log transformation. We look at the residual plots. One thing I want to mention here is that you might say, hey, it looks like there's big standard deviation in the middle and small standard deviation out here. We've got to take into account the fact that we have many more observations here at voltage 30 than we do at these other ones. It's very easy to get 2 together when you're only taking 3. Notice, don't forget this one down here. But it's very hard. The more you sample from a population, the more you get to see what the true distribution looks like. So if it looked like this and we had the same number of observations for each voltage level, that would be concerning. But of course, when you have smaller number of observations, it's much easier to get them clumped and to not really explore the whole width of the distribution. Much less probability of getting into the tails when you have a small number. So here is, we like our assumptions. Our assumptions look to be met. So at that point, we're going to go ahead and run, get the parameter estimates. So we'll run procgreg or procglm, get those parameter estimates. And then, of course, we want to interpret it. But first, let's go through the math of what's actually happening here so we can figure out how to interpret it. In office hours, I will go through, it's one of my favorite things to do, is a little chalk talk on why it is that we're looking at the median. When we do a log transform of y, our inference is actually on the median, and sometimes, and usually on the ratio of the medians. But let's check this out. So here we have, we're transforming y, so that's the log of y. Notice that x is not transformed, so we're dealing with a log linear model. And we check out, so we know, you're going to have to take my word for it for now, read the book, or come to office hours and watch the video of office hours. I'll break it down as to why it is the median. It's actually pretty cool. It uses a lot of the properties and characteristics that we've learned so far in that pseudo proof. So, so here is the first one is, what we want to do is, you might say, why this seems arbitrary. And it is arbitrary. It just so happens that if we look at this statistic, the parameters in this model cancel out in such a way that it's very easy to interpret. If I look at the ratio of the medians for x plus 1 versus x on the bottom. So for a 1 unit increase in x, how does the ratio of medians change? So think about that. Maybe replay the last 30 seconds or a minute here to really get to where these 4 steps are coming from. And we'll go on with the rest. You can go ahead and pause. This is the beauty of these videos, pause and move on at any time. But why am I looking at this statistic, the ratio of the medians for x plus 1 on top and x on the bottom for 1 unit increase in x? Because it's going to simplify very nicely, as you're about to see here. So let's look at it. So if this is the, notice that this is the regression equation for x plus 1. This is the regression equation, exponentiated regression equation for x, just using this identity right here. So that's the one for x plus 1. I've done x plus 1. That's the one for x. And now let's see what can happen here. Of course, the e beta naughts are going to cancel. So the e beta naughts cancel. I'm left with e beta 1 x plus 1 times e beta 1 x. Go ahead and distribute that beta 1, and you'll end up with e beta 1 x. We need our exponent. We need our exponent properties. So maybe go back and review that that calculus, that pre-cal. But at this point, very easy to see the e beta 1 x's are going to cancel, and that's why we chose this seemingly arbitrary statistic to measure, because it in our regression equations simplifies very nicely just to e to beta 1. So how do I interpret beta 1? I simply, in a log linear model, I simply exponentiate the beta 1, and a 1 unit increase in x, right, x plus 1, a 1 unit increase in x is associated with a multiplicative change of e to the beta 1 in the median of yx. So when you've studied this a couple of times, it's awesome if you get it the first time. I think it'll probably take 2, 3, 4 times and a little bit of practice to really understand and feel what's going on here. But after you have that, you're like, wow, this is really simple, as long as you're looking at the ratio of the medians here. So let's see a quick example with our voltage. And we can get confidence intervals very easily, the same way we've always gotten confidence intervals. You're going to get a confidence interval for beta 1. Beta 1 hat plus or minus a multiplier times the standard error from the parameter estimate table, just like we've always done. Or you can use CLB in SAS to get those, and then exponentiate the lower and upper limit, and you'll have a 95% confidence interval for this estimate, for the 1 unit increase in x, for the multiplicative change for 1 unit increase in x. Awesome. So interpretation, let's see at this one. We've done a log linear model. This is our slope right here, e to the, or not e to the, we haven't exponentiated it yet. This is just beta 1 hat, negative 0.50736. So here we go. The data suggests that for each 1 kilovolt increase, that's what x is measured in voltage, is associated with a decrease in time to insulation breakdown by a factor of e to the negative 0.507 equals 0.6. And remember, that's a multiplicative change. That's a multiplicative change. So, in other words, a 1 unit increase in voltage is associated with a 40% decrease, because this is 0.6. It means that the median for each 1 additional kilovolt, the median for that increase is 60% of the median of the one before that. So if you write that ratio out, it's just ratio of x plus 1 over the ratio of x, or the median of x plus 1 over the median of x equals 0.6, means the one on top is smaller, and of course that's 1 minus 0.6, a 40% decrease in time to breakdown. So a 95% confidence interval for that, I'm not sure it's 40%. I'm 95% confident that, let's go ahead and find a confidence interval for beta 1. So I can use that standard error, and I can use the fact I think we had 76 observations. So this is 76 minus 2 degrees of freedom, right? 2 because we have an intercept and a slope. There's only 2 parameters in the model. So you'd use a t multiplier with 74 degrees of freedom, and it'd be beta 1. So here it is right here. So this is beta 1 hat, that's negative 0.507, minus the t multiplier, that's a t multiplier for 95% confidence with 74 degrees of freedom, times the standard error. This is all stuff we've done in previous units, so just a little review. That's our lower limit, add here, that's our upper limit, and we get these two. If you exponentiate these like I've done here, then you've got an estimate for, a 95% confidence interval for this 0.6, and then of course that equates to a very interpretable 46% decrease, 1 minus 0.54, and a 32% decrease. So you can think of the negative as a decrease. So we're not sure it's 40, but we're pretty sure it's 95% confident. It's between 46% and 32%. So finally, we're going to, for that last question, we're going to interpret R squared. It is estimated that voltage explains about 51.36% of the variation in breakdown time of this insulation fluid. So very interpretable. This will be the next example that we go through, but that is a quick example of the log linear model. Excellent job. See you in the next video. Hi, and welcome back. In this one, we're going to be talking about the linear log model this time. Last time we did the log linear. Now we're going to transform the x. This is a linear log model. Let's check out the example. So a certain kind of meat processing may begin once the pH in postmortem muscle of a steer carcass decreases between 6.0 from a pH at a time of slaughter around 7 to 7.2. It's not practical to monitor the pH decline for each animal. It's expensive and hard to do. So an estimate is needed for the time, which is very easy to measure after slaughter, at which pH reaches 6.0. To estimate this time, 10 steer carcasses were assigned to be measured for pH at 1 of 5 times after slaughter. So we've got 10, we're going to have 2 repeat at each time and measure their pH levels. So we can build a model that hopefully will be able to let us just look at the time and estimate what the pH is of the carcass. So here's our model. Actually, this is the no transform. This is just the linear model. If we try that, right, we're going to plot the data and we just try it without just fitting a normal line to it without any transformations. We can look at our residual plots, and notice here we can kind of see the curve, but in the residual plots we really see it. Looks like standard deviation's probably okay. Maybe a little bit hint of increasing standard deviations. We're going to assume that those are all right, but that the trend is curved. So as time increases, the pH first dips and then increases at some point. So what are we going to do for that? There's a lot of different remedial measures we could do. One would be a different kind of transform, but this one is going to be a log transform on the x that you can see here. So notice this is linear log because it's no transform on the y, so that's linear, and log on the x. Let's see what that does. So we're going to plot the data after this. Again, this is trial and error. So right after the log transformation, we plot again, look at the residuals. Ah, so much nicer. There's only 10 observations, so it's not going to look perfect, and you would love to have more and more observations, but that's pretty good for only 10 observations. It's certainly better than the one we saw before. So if we're satisfied with the assumptions are being met, we can fit the model. There's our parameter estimates. There is our beta 1 that we're about to interpret, and that's our intercept. That's our beta 1 on the log scale there. So let's see mathematically what this is going to equate to, just like last time. So this time what we're going to do is look at the difference in means instead of the ratio of medians, and we'll see why here in just a second. But this is the top one is the model. This is a more formal written version of the model. We're modeling the mean, mu, the mean of y, this time of a transformed x. So what's going to be, again, this may seem arbitrary, but the reason why we're doing it this way and not the ratio of the means, but the difference of the means, is again because the way that our model is specified here, it's going to be very convenient to look at this statistic, so or parameters that may be. So when we look at the difference in means, it's simply a regression equation of the, oh, I'm sorry, I forgot a very important part. And we're not going to look at a 1 unit increase in x, we're going to look at a doubling of x. So as you may have guessed, anytime you're dealing with the log, that's kind of a multiplicative relationship. And anytime you're dealing without the log, just the identity, differences and additions and subtractions are more natural. So here, instead of looking at a 1 unit increase in x, we're looking at a doubling of x. And instead of looking at the ratio of medians, we're looking at the difference of means. Why do we do all that? Because it becomes very convenient in the end to interpret beta 1. So here it is. So if I simply now group, oh, I'm sorry, just subtracting the beta naught. So that's beta naught minus beta naught. We're going to end up distributing this subtraction sign. So again, that's beta naught minus beta naught. So the intercepts have canceled each other out, which is nice. And then we've got beta 1, and we have these ideas of logs. So you might go back and look up your log properties, but I'll give you a quick review of them here anyhow. I'm going to, oops, my animations are a little funky there. But let's just go ahead and take it from the top down. This will be beta 1 log 2x minus beta 1 log x. I'm going to factor out the beta 1. That's beta 1 in both terms. Factor out the beta 1. And I get a log 2x minus log x. Right? And we know that the difference of logs is the same as a single log with the ratio of their arguments, the argument being 2x and x. So that's probably the trickiest mathematical step in this particular derivation. But I factor out the beta 1s. I've got a log minus a log. It's just the log of the ratio of their arguments. That's very nice because 2x over x is just x. So, or is just x. So, I'm sorry, 2x over x is just 2. The x's cancel, so we left with beta 1 log 2. And there we have it. So the difference of means is estimated to be beta 1 times the log of 2. And notice how natural this is. If you're in a situation where a 10 times x is more natural, like whatever situation you're in, like, well, the scientists usually measure that as 10 times increase. Well, then just make this a 10 times, and that'll reduce to a 10 there. That'll equal out to be a 10. If you want 20 times, make that a 20. 100 times, make that 100. So very natural to kind of change that statistic to get it to the scale that you want it, but it is of the difference of means of y, and the estimate of that difference of means is beta 1 times the log of 2 for a twofold increase in x. So a doubling of x results in a beta 1 log 2 unit increase in the mean of y. And we can very easily build a confidence interval for that when that becomes a beta 1 hat when we're estimating it using the sample, simply by doing what we did last time. And that's taking beta 1 hat plus or minus a multiplier times the standard error of beta 1 hat. Show you an example of that right here. So here is, again, the results of us fitting beta 1 hat for the meat carcass example. There's our beta 1 hat. And so what we're going to look at here is, that is the regression equation. And so the data suggests, if I want to interpret again that beta 1, suggests that the predicted pH decreases by, sorry, this is beta 1, negative 0.72556, right there, 0.72556 times log 2. That equals negative 0.503. That's not a multiplicative change, that's the estimated difference in the means. So one more time, the data suggests that the predicted pH decreases by 0.503 for each doubling of time. Very important. For each time you double it, the estimated pH decreases by 0.503. A 95% confidence interval is just the same way we did it before. There's my estimate plus or minus a multiplier times the standard error. That's exactly, if you backtrack, you'll see that's what we've got right there. So that is my best estimate, a 0.503 decrease. I'm 95% confident that that decrease will be between 0.558 and 0.448 pH units. Just interpreting that R squared there at the very end, time explains about 98.23% of the variation in pH for these steer carcasses. So you think you've got a pretty good model, you've got a pretty narrow confidence interval. That's, of course, probably subjective, but you can estimate practical importance just by checking this guy out. and very easy to interpret the coefficients of a linear log model. And that's what we looked at in this video. When we come back, we will look at it's my favorite example. I'm not partial to a particular transform, of course, but my favorite example is coming up. It has to do with Bush and Buchanan back in the election quite a long time ago, but back in the 2000 election. But stay tuned for that. That's in the next video. This was the linear log model. Hi, in this video we're going to talk about the log-log transformation. And we're going to do it with a really cool example that deals with the presidential election of the year 2000. And that you had Bush versus Gore versus Buchanan. Let's go ahead and take a quick recap of what that looked like. This was the election, so it's in November, around Super Tuesday of 2000. It all came down to Florida. So everything else was tied up electoral college-wise, so it came down to Florida late night. And Gore was projected the winner. Like the CNN came out, we project Gore to be the winner. And then they were like, wait a second, make that Bush. Bush is projected to be the winner. And then it got kind of late into the night, and Gore said, okay, that actually looks right, so I'll concede. He had a very nice concession speech. And then they kept counting the votes, though, right? Throughout the night, they keep counting it, and then more and more Gore came in, and so Bush's lead was cut to 1,738 votes. So then Gore says, well, not so fast. Let's go ahead and retract that concession right now. And so then they kept, automatic recount was invoked. So they went back and recounted them, kept counting and then recounted. And Bush's lead was cut to less than 400 votes in the entire state of Florida. So a strange phenomenon, when the people went back to look at this, a strange phenomenon was discovered. Of course, in the end, just to kill the suspense, yes. Bush, of course, won, but then won by less than 400 votes. And so when we go back and look at it, when we have a little more time to do a little analysis, we can see what might end up happening. So we can look at Palm Beach County. What we're going to do in this example is look at the log-log transformation, don't worry. But we're also going to incorporate a lot of the other things we've looked at in simple linear regression so far. Confidence intervals, prediction intervals, outliers. So let's go ahead and check that out. So in this county, Buchanan had suspiciously large number of votes in Palm Beach County. And how can we see that? We'll see a scatter plot of that here in just a second. On closer inspection, there were also a suspiciously large number of ballots that were thrown out because of two chads. Remember the hanging chad? This was part of it because two chads were punched out and only one is allowed. So it's called the butterfly ballot, and this is what it looks like. So here's what the whole idea was. As you had Bush up here, wanted Bush, you'd poke that top one out. If you wanted Buchanan, you'd poke that one out. If you wanted Gore, you'd poke that one out, so on and so forth down the way. So what they ended up finding out is that a lot of times these two, the second and the third one here, were punched out. And the idea was that, or some people were surmising, especially in Palm Beach County, this was the ballot in Palm Beach County, that people really wanted Gore. This was the hypothesis. People wanted Gore, and they saw he was second down the list, so they knocked that Chad out. And then they were like, oh, no, wait a second. I knocked that Chad out. That's for Buchanan. So they went ahead and hit the correct Chad, which was third. So they had both of these punched out. And then some people who did not recognize their mistake might have just punched out Buchanan and might have just punched out Buchanan thinking they were going for Gore. So that was why they thought that there was a huge amount of Buchanan votes in Palm Beach County, was because a lot of them they thought were supposed to go for Gore, and people just thought, oh, Gore's number 2, so I'll punch out number 2. So let's try to quantify what the difference was. Let's try to adjust for this potential mistake. So our goal here is to estimate how many of the votes for Buchanan were meant for Gore. So here's the strategy. We'll build a prediction interval for Buchanan. So we're going to look at the Bush votes versus Buchanan votes. So Buchanan will be Y and Bush will be X. Can we learn something about the number of Buchanan votes per district given the Bush votes? And so we'll need a regression equation for regressing Buchanan versus Bush votes. we will regress Buchanan on Bush votes, like we just said there. From the forthcoming prediction interval, we can estimate how many votes Buchanan should receive given the explanatory variable. So remember, the prediction interval is for a single draw, a single observation. That's what we're doing here with Palm Beach County. We want to say, well, what is the maximum that we think if the trend is true, if the trend is conserved for Palm Beach County for Bush votes versus Buchanan votes, what is the maximum we should expect to see from any given county? And then simply, once we have that, we'll see how many actually got, how many Buchanan votes there actually were, subtract the prediction, the highest that we think would have been reasonable, and we'll see if that's a considerable margin. So that's top level. That probably didn't make a lot of sense to me just talking about it. If you just got the idea that we're looking at Bush votes versus Buchanan votes, we're going to get a prediction interval. That prediction interval is going to give an estimate of how many Buchanan should have gotten. We'll see how many he did, subtract the two, and get an estimate of how many may have been meant for Gore. So here it is. Here's the picture. This should bring it a little together more. Each one of these is a district or a county. And you can see that that indeed looks like, for just judging from it, that as Bush votes get bigger, Buchanan votes, more people vote for Buchanan. Until you hit up here, so don't forget about this point, that is Palm Beach County, which does not go with the trend. So you have two decisions to make here, really, is maybe Palm Beach's county is just a lot different than the other ones. In that case, we're not really looking at the same population here, and we should delete that guy. But our analysis is about him, and that butterfly ballot is wreaking havoc on this trend. So let's use it to see what we can do. Let's use our structure framework of regression that we've had so far and see what we get. So if we just ran a regression, this would be our beta 1 hat. That's our regression coefficient for the number of Bush votes. And notice what we've got so far is when we look at the residual plots, right, before we actually run that, before we actually use those estimates, we want to make sure our assumptions are met. And well, what I've put these parallel bars on here for is to show that it's actually, we have evidence, pretty strong evidence of increasing standard deviation. As Bush votes gets bigger, it does look like the trend may be increasing, but it also looks like the standard deviation is increasing, and that is going to create a problem for our prediction intervals, because we won't know how to estimate the MSE. Should it be very small? Should it be big? Should it be somewhere in between? What exactly should that be? So there's just an example of the residual plot from that 3x3 plot, the fit diagnostic plots from ProcReg and ProcGLM. Noticing that our outliers are still on there, so don't forget about that guy. So what we want to do is look at, that's the data with the outlier. This is another step you would do, and then you want to look at the data without the outlier. So this is the one without Palm Beach. We've just deleted that one. What we're going to do to delete that one is because we don't want that one to have influence when we're trying to build the trend. If we're assuming that Palm Beach has the same trend, we'll just take it out, use the other ones, and then we can build our prediction interval that way. So that is the regression coefficients with Palm Beach. This is the ones without. We still may have some problems here with our assumptions, so we may not want to use this to interpret this this regression coefficient right now. But I do want to show that just kind of a separate topic that's come up right here. Notice that this line looks like it has more slope than this line. But also notice that the scales have changed on the side. And you can see the slope right here. This slope is 0.00492 and this slope is 0.00348. So deleting this influential point, which we'll study influence in the next chapter, but deleting this influential point actually decreased the slope, but it looks like it increased simply because the scale changed on the x and y axis, or just on the y-axis here. So my point there is be careful. You can be duped and you can make a mistake just by looking at plots. Make sure that the scales are the same, and I've been guilty of that and a victim of that on more than one occasion. So make sure that when you're trying to compare plots that the scales are the same. But so that was the point there. And notice that, but notice that the r² has gone up considerably, namely because that big residual is not in there anymore. So we'll assume that Palm Beach County data is an error and proceed with the model without the outliers, without Palm Beach to get these estimates. This is another look at the residual plot from the plot without Palm Beach County. You can see clear evidence of increasing standard deviation for increasing Bush votes, counties with Bush votes. So we'll try a transformation. So this was me trying the log. I always said it was trial and error, right? So this is me trying a log linear model. Looks like we still have increasing standard deviation, and now we've introduced some sort of curved trend. So that didn't work too well. So we don't like that one. Then I tried a linear log model, right? Linear in Y and log in Bush. And that one also looks like it's introduced some curve to it and still increasing standard deviation. No good. But hold your horses, because here it comes. When we try a log-log model, right? A log-log model here, it would look like we had linear trend, just increasing standard deviation. A log-log model might help, and look at that. I don't know if you'll see a simple linear regression model with the assumptions met just any better than that. There are the residuals. That's the residual plot. Everything looks great. Constant standard deviation, random cloud around 0. We would indeed, I don't think I have that on here, but look at the histogram and QQ plot of the residuals to make sure that they're normal. This code, the SAS code for this is available, so you can check that out. But these are parameter estimates that we think look good. Again, they're on the log scale for the X and the Y, but we are satisfied, we should be very satisfied with this estimate and with this standard error. But now, of course, how do we interpret a log-log model? So, so let's go ahead and do both interpretations. We're going to interpret the actual model and the regression coefficient, but here's how we would use it. There's the log-log model, right? We can get an idea of how many Buchanan votes are there if I can input how many Bush votes are in there. And note from before that Bush votes in Palm Beach County were 152,846. So all we're going to do is plug that 152,846 into here and get an estimate for the log Buchanan and then transform that out. So you can see right here the log of 152,846 is 11.93. So this whole thing here becomes 11.93. We do the math on that. We get log Buchanan equals 6.38. So we exponentiate both sides. So the Buchanan votes, the estimated Buchanan votes should be about e to the 6.38, and that's about 589 votes. But very intriguing, right? Because if you go back and look at the ones before, he actually got over 3,000 votes in Palm Beach County. So our best estimate is 589, but that's an estimate. So let's be as conservative as we can and look at those prediction intervals, and namely the top prediction interval. So the 95% prediction interval now for Buchanan votes versus out of Bush votes of 152,000, which is what he got in Palm Beach County, is 251 to 1399 votes. So 1,399 are the highest plausible value that we think could have come to. We're 95% confident that that is that's the most plausible number of Buchanan votes, the highest plausible number of Buchanan votes that we could have seen if this trend between Bush and Buchanan is consistent for Palm Beach County, which is what we're assuming. Wow. So what are we going to do? Notice here we said that's our prediction interval, just so we can keep track of it. The actual vote for Buchanan was 3,407, and the largest predicted with 95% confidence value was 1,399. Therefore, we can predict that 3,407 minus 1,399 equals 2,008 votes were not meant for Buchanan. Doesn't mean, this is all speculation, but based in data, with reasonable assumptions, you could argue. So were all 2,008 of those meant for Gore? They may not have been meant for Buchanan, but were they meant for Gore? We don't know. But it certainly is intriguing. So if at least 400 of these were meant to be cast for Gore, the world could be a very, very different place. Gore might have been elected as president, and certainly, for better or worse, a very different place. So, amazing. Now let's interpret the log-log model. So we'll finish out this video by looking at the interpretation. So here it is. We've seen these before. Now we've got the log on the response and the log on the explanatory variable. So there's our model. Again, why are we looking at the median of y at a doubling of x versus the median y for just x? Because the simplification of this model is very, very simple once again if we look at the statistic. If we looked at the difference of medians, we wouldn't be able to have a very nice interpretation of beta 1. But you'll see if you pick this interpretation, that was always a question for me. Wow, that's kind of a random statistic there. The only reason why we're picking this is because everything falls out of the simplification here very nicely when that happens. So we're looking at the ratio of the medians for a doubling of x. So notice what happens there. The beta knots cancel, e to the beta naught. So this is really e, if you remember the pre-cal rules, this is e to the beta naught times e to the beta 1 log 2x. And that's e to the beta naught times e to the beta 1 log x. Following that through, the e to beta naughts cancel. And then we subtract, if we divide the bases, then we subtract the exponents. So subtracting those exponents and factoring out beta 1 gives you this. Then it's just what we've seen before. We're going to say that that is the log of 2x over the log of 2x over x. So the log of 2x over x is just the log of 2. And we take e to the beta 1 of that. Remember that you can take, when you've got a coefficient of this log, it's the same as raising the log to that power. So the logarithm is an exponent. So this is just another rule of exponents, is this beta 1 can be put up here to this to the 2 to the beta 1. And of course, e to the log to the beta 1. The logs, the e and the log cancel, they're inverses. So we just get left with 2 to the beta 1. So interpretable. And that's why we picked this statistic, this parameter, to look at. The median of the doubling of x divided by the median of y at just x, it reduces to 2 to the beta 1. And again, if you wanted that 10-fold x or 100-fold x, that would just be 10 to the beta 1 or 100 to the beta 1. So very, very interpretable. And this is the log-log transformation. So interpretation here, long story short, is a doubling of x is associated with a 2 to the beta 1 multiplicative increase in the median of y. And if we wanted to see a quick example of that, we can use the Bush-Gore example that we just saw, Bush-Gore-Buchanan. There was the beta 1. So if we simply take that 2 to the beta 1, we will get inference on the median of Buchanan votes. So we had this guy. So therefore, a doubling of the votes for Bush equates to a multiplicative change of 2 to the 0.731, which is 1.66, in the median of the distribution of Buchanan votes for the given Bush tally. So in other words, this is how I like to look at it. A doubling of votes for Bush increases the estimated median of Buchanan's votes by 66%. So it was a multiplicative change of 1.66. That's simply an increase of 66%. Is that significant? Well, we certainly see that it's significant here with that p-value, but look at the confidence interval. That should agree. A 95% confidence interval for beta 1 is simply, there's beta 1 plus or minus a multiplier, which in this case is about 2 times the standard error. It's that 0.03597 is that 0.036 rounded right there. There is my lower limit, there is my upper limit, just like usual, and I get 0.659. Raise 2 to each of those, right? 2 to the 0.659, 2 to the 0.803 will give you about 1.58 and 1.74, which equates to a 58% increase to a 74% increase. Both of them are increases, so we know that it's significant. So we can't, this is suggesting we can't, that Bush votes are associated to the median of Buchanan votes. And of course we can interpret the R squared. It's estimated that the number of Bush votes explains about 86.5% of the variation in the number of Buchanan votes. Looks like we've got a pretty informative model here. So in summary, that was my big Bush example, Bush-Gore-Buchanan example. I love it. It's a little bit of a long video. Thanks for sticking through it. But in summary, this is the real takeaway from this chapter for log transformations anyhow. We have a log linear model. That is the interpretation of the log linear model. It's a 1 unit increase in x. Notice the x is not logged. So that makes it a 1 unit increase in x. It's associated with a multiplicative change because the response was logged of e to the beta 1 in the median, not the mean of yx. The next one, we are not logging the response. We are logging the explanatory variable. So that's where a doubling, anytime you're doing this explanatory variable, the log, it's a doubling or a triple or a quadruple or a tenfold. A doubling of x results in a beta 1 log 2 unit increase in the mean of y because we didn't transform y. So it's back on the difference of means. Great. Then finally, the last one is a blend of both. You've got the log-log model. So it's a doubling of x because we logged the explanatory variable is associated with a 2 to the beta 1 multiplicative increase, multiplicative change, I guess I shouldn't say increase, multiplicative change in the median of y. Again, the median of y because the log is the log is on the response as well. In office hours, I'll show why it is on the median. So the big question might be, why is it that that it's on the median, not the mean of y when we log x? And there's a very nice, cool explanation for that. Great work, long video, but lots of information. Excellent job, very important. I'll see you in the next one. Nice work. Hi, in this video, we're going to look at the lack of fit test for a regression model. So this is going to be a simple linear regression model, just so we can see it and plot it. Here we have a group on the x-axis, and we have scores on the y-axis. And as you can see, we have 4 different groups, and we have repeat observations for the score at each group level. So in order to do a lack of fit test, you must have this estimate of pure error, which is given to you from repeat observations at individual group levels. So that's what we have here. Of course, we could build, I want you to go back and think about the ANOVA that we studied before. ANOVA, that's exactly what we can do here, right? We've got 4 groups. We're looking to see if there's a difference in means between any pair, between at least one pair of the groups. We could run a simple ANOVA. Of course, in order to do that, we're going to have to fit, in this case, 4 different, a model that has 4 different parameters. Mu for group 1, mu for group 2, mu for group 3, and mu for group 4. Contrast that, so that takes 4 parameters. Contrast that with a linear regression model. It looks like we can recover the mean relatively well here, the mean of these assumed normal distributions of scores for subpopulations of group. Looks like we could recover the mean of those normal distributions simply by taking advantage of the fact that those means look to be linearly related. So instead of recording a separate mean for each one, let's just essentially record a recipe or a map on how to get to those, which is known as the regression equation. So once again, we can individually record, try to estimate a mean for each group, or we can come up with the relationship of the means, and that would be good for any for any group, as long as we're assuming here, of course, that group at that point isn't just a group number, but a quantitative meaning. So 2 is twice 1, and 4 is twice 2. That group is actually a quantitative variable. Because again, if it's not, we can't use linear regression if we don't have a quantitative variable on the x-axis. So we're going to assume here that we have an x-axis that's quantitative, that variable is quantitative, and we're going to compare fitting 4 parameters to fitting a simple linear regression model that has 2, the intercept and the slope. So let's check it out. So here is both models as we would do in GLM. You can do either one. This one on the left here is the separate means model. You can see that it's fit a separate mean for each group. And notice that we had 24 observations, right? Really go back and think about those ANOVA models. We have 24 observations, and we had 4 parameters that we fit. So 24 minus 4 is 20. That's where we see our degrees of freedom for the error right there. And remember that this row is going to be so important in our discussion here. This row is the equal means model. That's equivalent to having fit, I'll go back to this plot here, having fit the mean, which the mean of all of these 24 observations looks to be around 12 or something. We could find it exactly, but right around in the middle here, that's the equal means model. Not a very good model, but it's the model at which we're going to compare things in an ANOVA. So really maybe go back and read that and kind of brush up on the equal means model. But remember, we're going to draw a line straight across here. Look at the distance that represents the mean. Look at the distance between the observation and that. That's our residual, and that equal means. Square that for each of these 24, add them all together, and that would be this number right here, 1320. That is the sum of squared residuals with respect to the equal means model, where the same estimate is across all x values. Notice that it's the same for both, because both of these ANOVA tables are comparing a different model to the equal means model, and it's saying, hey, is it better than essentially nothing? Is it better than just this guess of the mean? So this one here, just to kind of take us back through it, is we say, okay, well, the amount of error, the sum of squared residuals with the equal means model is 1320. If I fit separate means, it reduces that 1320 all the way down to 81, but it did take me 4 parameters to get there. So I subtract that. 23 minus 20 is 3. That's how many more parameters there are in the in the separate means model than there are in the equal means model. There's 3 more. This takes 1 parameter, this takes 4, so there's a 3 difference. And for those 3, we explained 1320 minus 81, 1,238.916667. From that, we divide these and we divide these across in the rows to get 4, 12, and 4. We divide 4, 12 by 4 to get 101, and we see that that's a very significant result, meaning that it looks like the separate means model fits better, that we learned something about group membership. We learned something about score from group membership, that it fits better than the equal means model, which may not be saying a lot, right? The equal means model should be pretty easy to beat. So then we come over here and say, well, all right, well, it looks like the assumptions of simple linear regression are met as well. So how well does that do? Well, we're still comparing it to 1320. This one knocks it all the way down to 83. And we say, okay, well, of course it's not going to do as well as if we fit each group, let it have its own mean, but it does pretty well, and it takes 2 less parameters to do that. So notice that this is 24 minus 2 because of an intercept and a slope. I'm not fitting a separate parameter to each group. I'm only fitting 2 parameters and letting it go for all the groups. In this case, there's 4. If there were 10 groups, we'd really have a savings. But we have 24 minus 2 is 22. That's why this one is bigger, but bigger than this 20 over here. And the 83, of course, it's not going to do quite as well, but it does almost as well. And so notice that while up here, so I subtract these and subtract those to get the 1236. Up here, it took me 3 extra parameters to get 1,238 extra. Here, I'm getting 1 parameter. 1 extra parameter is giving me 1,236 extra. So which of these models, how good a fit is the linear regression model? That's what we want to ask. And right now, this is saying, this is really my whole point I've been building up to this whole time here. This is it. Is this ANOVA model is saying that the regression model is better than the equal means model. Great. Again, what does that really tell you? It just tells you it's better than almost no model. It's better than the simplest model you could find. So what we'd like to do instead is maybe compare the simple linear regression model to what we might think the best model is. The most ramped up model, the one with the most parameters in it, the one that has the most opportunity to explain more. How well do these two compare? Rather than just compare it to the ho-hum equal means model, let's really have a tournament and let's have this model compete against a really good model. That's what we're going to do here. So that's basically reading down there what I just said. The question is, does the simple linear regression model do about as well with 2 parameters as the separate means does with 4? We want to evaluate the linear regression model against a really, really good model. It doesn't really tell us so much about comparing it to the equal means model. It could still be a terrible model. It could still be the equal means model. So that's what we want to do here, is let's pit these two against each other. Great. So that is what you're looking at here. Ta-da! This is the lack of fit test. So what we're going to do is build our own ANOVA. Once again, we're going to build our own ANOVA model, but instead, the ANOVA model allows us to compare 2 models against each other. It just so happens that when we run it in SAS or in many computer programs, we got to be careful. But in SAS, down here, the last row, this corrected total, is always the equal means model. The last row there is always the equal means model. So this one's comparing the separate means model to the equal means model, it won. This one's comparing the linear regression model to the equal means model, it won. So what we're going to do is use that same idea, the F statistic, but notice that my bottom one here now, I'm going to make my linear regression model. And I'm going to make this one here the separate means model. So now I'm pitting these two against each other. I'm pitting these. So the equal means model has nothing to do with this lack of fit test now. I'm just saying, hey, let these two compete against each other. And when we do that, of course, these two sum of squares, as we saw before, are pretty similar. Their difference isn't very big. The separate means model has 2 extra parameters. We find the mean squares, we divide them, we get the F statistic, and here we fail to reject. But we got to remember what we're doing. We're comparing the linear regression model to an awesome model. And this failing to reject is saying there's no noticeable difference between the two, which is really good news for the linear regression model, right? So up here we wanted to reject because we said, hey, okay, the linear regression model is better than a crappy model, but a terrible model. And down here it's saying it's a different hypothesis, right? It's saying, hey, let's look at the linear regression model versus the separate means model. And we're saying there's barely any difference at all. We can't detect a difference, not a significant difference. That's good news. Both of those are good news for the linear regression model. And I would argue that the lack of fit test, which is what we're looking at down here, is more informative. It's saying that that there's no noticeable difference, that there's no lack of fit in our linear regression model, assuming here that the separate means model fits the best it can, because it's got the most parameters to try to reduce those sum of squared residuals. So conclusion, there's not enough evidence to suggest the linear regression model has lack of fit with respect to the separate means model. Add your p-value onto that, and you're ready to go. Note the description in the book breaks this down into different rows and different sum of squares. They're different between sum of squares. This is equivalent to that, and this is essentially what we're doing in the end. If you have any more questions on that, I can answer those. But all we're doing is pitting two models against each other using an F-test. So I wanted to leave you with this idea is, I got to thinking about it, and it was a World Cup when I was starting thinking about it. And so if this doesn't help you, it's all right. But if it does, it may really help. So a heuristic description of what we're doing. Let's say that I want to compare soccer players. So if I want to compare soccer players, there's Messi. Messi is arguably the best soccer player in the world. And then this is John. John is on my high school soccer team. I actually went to W.T. White. This guy's on my soccer team. He's a good soccer player, but not nearly as good as Messi. So the idea here is if we're picking our players for a soccer team, you don't get to see any of your prospects play, but you do get a piece of relative information. Which piece of information would be most useful for you? So you're trying to pick a team. Which one would be most useful to you? If I came out and said, hey, the player's skills that we're talking about are indistinguishable from Messi's. Meaning he is almost as good, if not as good as Messi. When I'm comparing the two, I can't tell a difference, aka failed to reject. Or if I came out and said, okay, the player is better than John. Which one would you prefer to know? Which one's telling you more about this player? Because they're both true, right? The player is better than John, or would you rather know that he's indistinguishable from Messi? That's the difference between what we're looking at here. The player that we're looking at is your model. So which model do I want to use? John is the equal means model. Messi is the separate means model. Which one do I want to compare my linear regression model, my player, to? And this one would be the ANOVA. When you run an ANOVA, it just simply tells you it's better than the equal means model. So saying your player is better than John. But when we compare it to a really, really good model, like the separate means model, certainly better than the equal means model, that's equivalent to the lack of fit test. So I've got one more slide here to kind of keep this idea going. But that's what we're doing here is we're comparing our linear regression model to a really great model. And if we fail to reject, it means that we fail to reject to see a significant difference between the two, which is really good news for the linear regression model. So that's what I was doing here. We have the equal means model, EMM, the linear regression model, I'm going to call that LRM, and the separate means model, SMM. That's what an ANOVA looks like. Remember, that's the equal means model, and that is your linear regression model, the one we just looked at. And this is when we're doing that, that is, again, the equal means model, and that is the linear regression model. And at the end of the day, it's just saying, hey, we rejected. Oh, great, we rejected. That means that there is significant evidence to suggest that the linear regression model, there's really strong evidence to suggest the linear regression model fits better than the equal means model. Great, that might not be telling. Maybe it just fits marginally better. So that's like comparing your model to John. Okay, great, not bad, I'm glad it rejected. But the lack of fit test doesn't have the equal means model in it. It takes our linear regression model and compares it to an amazing separate means model. And if we fail to reject there, that's like comparing our model to Messi. And so the lack of fit test, if you have these repeat observations, can be a really good way to measure fit for the linear regression model, or lack of fit as it is, how appropriate your model is. So that's it.